Acids and bases are substances we encounter in everyday life, often without realizing it. An acid is a substance that can release hydrogen ions or H+ ions in water, while a base can accept those ions or produce hydroxide ions or OH- ions. This difference affects how they behave and how they feel. Acids often taste sour, like lemon juice or vinegar, while bases tend to feel slippery, like soap. Chemists use the pH scale, which ranges from 0 to 14, to describe how acidic or basic a substance is. A pH below 7 is acidic, above 7 is basic, and exactly 7 is neutral, like pure water. What happens when you take an antacid tablet for an upset stomach? Stomach acid is naturally acidic and helps digest food, but too much of it can cause discomfort. Antacids are basic substances that react with the excess acid in your stomach, reducing its acidity and providing relief. This type of reaction, called neutralization, produces water and a salt. Understanding acids and bases helps explain not only common experiences like this, but also many processes in cooking, cleaning, and even how our bodies function. This slide highlights the real-world impact of acids, specifically focusing on how acidic drinks can affect dental health. As we discussed earlier, acids are substances that release hydrogen ions, H+, in solution, and one of their key chemical properties is their ability to react with and break down certain materials. Tooth enamel, the hard outer layer of our teeth, is primarily composed of a mineral called hydroxyapatite, which contains calcium phosphate. Although enamel is very strong, it is vulnerable to attack by acids. When we consume acidic beverages, such as soda, sports drinks, or even fruit juices, the acids in these drinks can begin to erode the enamel, a process known as demineralization. The example shown in this slide illustrates the consequences of prolonged exposure to acidic drinks. Frequent consumption, especially in large quantities, keeps the mouth in an acidic environment for extended periods. This prevents saliva, which normally helps neutralize acids and repair early damage, from effectively restoring the enamel. Over time, repeated acid exposure leads to thinning of the enamel, increased tooth sensitivity, discoloration, and eventually tooth decay or tooth loss. This is not just a chemical concept. It is a biological and health-related issue directly tied to our daily habits. From a chemistry perspective, the key takeaway is that lower pH means higher acidity, and many soft drinks have pH values well below 7, sometimes as low as 2 to 4. At these pH levels, the concentration of hydrogen ions is high enough to dissolve the mineral components of enamel. Additionally, sugars in these drinks can be metabolized by bacteria in the mouth, producing even more acids and accelerating the damage. Therefore, understanding acids helps us make informed decisions. Limiting acidic drink intake, rinsing with water after consumption, and maintaining good oral hygiene can significantly reduce the harmful effects. This slide serves as a powerful reminder that the chemistry of acids is not just theoretical. It has direct and visible consequences in everyday life. This slide presents the pH values of common substances, helping us connect the abstract concept of acidity and basicity to materials we encounter in everyday life. The pH scale ranges from 0 to 14 and is a measure of the concentration of hydrogen ions, H+, in a solution. Lower pH values indicate higher acidity, meaning a greater concentration of hydrogen ions, while higher pH values indicate more basic or alkaline conditions with lower hydrogen ion concentration and higher hydroxide ion concentration, OH-. At pH 7, such as in pure water, the solution is neutral, where the concentration of H+ ions equals the concentration of OH- ions. As you move up the scale from 7 to 14, substances become increasingly basic. As you move down from 7 to 0, they become increasingly acidic. Let's focus on two familiar examples highlighted on the slide: lemon juice and household bleach. Lemon juice has a pH of around 2, placing it firmly in the acidic region. This means it has a relatively high concentration of hydrogen ions, which gives it its characteristic sour taste and its ability to react with certain materials, such as gradually eroding tooth enamel, as discussed previously. On the other hand, household bleach has a pH of around 12, making it strongly basic. At this high pH, the concentration of hydroxide ions is much greater than that of hydrogen ions. This strong basicity is what gives bleach its effectiveness as a cleaning and disinfecting agent, as it can break down stains, organic matter, and microorganisms. An important takeaway from this slide is that the pH scale is logarithmic, meaning that each unit change represents a tenfold change in hydrogen ion concentration. For example, a solution with a pH of 2, like lemon juice, is 10 times more acidic than a solution with a pH of 3 and 100 times more acidic than a solution with a pH of 4. Similarly, household bleach at pH 12 is 10 times more basic than a substance at pH 11. This highlights how even small differences in pH correspond to large differences in chemical behavior. Understanding where substances fall on the pH scale allows us to predict their properties, their reactivity, and their effects in both chemical systems and everyday life. Acids have a sour taste and turn blue litmus paper red. Examples of acids include hydrochloric acid, sulfuric acid, nitric acid, acetic acid, citric acid, carbonic acid, hydrofluoric acid, and phosphoric acid. By convention, acidic hydrogens are written first in the chemical formula. These are represented by the first hydrogens shown in red in each formula of the listed acids. Citric acid has 3 acidic hydrogens, meaning it is a triprotic acid. Note that the additional 5 hydrogens in its formula are not acidic. Bases have a bitter taste, feel slippery, and turn red litmus paper blue. Examples include sodium hydroxide, potassium hydroxide, sodium bicarbonate, sodium carbonate, and ammonia. Note that not all bases contain hydroxide ions or OH- ions in their formula. I will discuss more about it in the following slides. Arrhenius defined acids as substances that increase the concentration of H+ ion when dissolved in water. This is why acids are also called proton donors, a concept later proposed by Bronsted and Lowry. One of the topics covered in Chapter 12, Atoms, was the chemical symbols of elements. Here, the capital H is the chemical symbol for hydrogen. The superscript 1 on the left side of the symbol represents the mass number of hydrogen. The mass number equals the sum of the number of protons and neutrons. The subscript 1 on the left side of the symbol represents the atomic number of hydrogen, which is equal to the number of protons. With this information, we can determine the numbers of electrons, protons, and neutrons in a hydrogen atom. Hydrogen is the first element in the periodic table, so its atomic number is 1, meaning it has one proton. Since a neutral hydrogen has no net charge, it must also have one electron to balance the positive charge of the proton. Because the mass number of hydrogen is 1 and the number of proton is 1, the number of neutron is 0. Therefore, a neutral hydrogen atom has 1 electron, 1 proton, and 0 neutrons. Now, consider the H+ ion. The hydrogen ion has a positive 1 charge because it has lost its only electron. Fill the blanks for the hydrogen ion. It has 0 electrons, 1 proton, and 0 neutrons. Because the H+ ion consists of only 1 proton, it is often simply called a proton. From this point on, we will refer to the H+ ion as a proton. A monoprotic acid is an acid that releases 1 proton per molecule. Hydrochloric acid and nitric acid are monoprotic acids because each releases 1 proton per molecule. A diprotic acid is an acid that releases 2 protons per molecule. Sulfuric acid has 2 acidic hydrogens, so it is a diprotic acid. Note that the release of the first proton from sulfuric acid occurs completely, which is represented by a single arrow, whereas the release of the second proton occurs only partially, which is represented by a double arrow. Arrhenius defined bases as the substances that increase the concentration of hydroxide ion when dissolved in water. Bases are also called proton acceptors, which was suggested by Bronsted and Lowry. Sodium hydroxide, potassium hydroxide, and calcium hydroxide contain hydroxide ions and release them when dissolved in water. So they are all bases. However, there are bases that does not contain a hydroxide ion. Ammonia accepts a proton from a water molecule, becomes ammonium ion, and leaves hydroxide ion behind. Even if ammonia does not contain a hydroxide ion, it produces one by hydrolyzing a water molecule. So the ammonia is a base. The hydrolysis of water molecule by ammonia is represented by this equation. This slide introduces the concept of the strength of acids and bases, which refers to the extent to which these substances ionize or separate into ions when dissolved in water. It is important to understand that the terms strong and weak do not describe the concentration of an acid or base. Instead, they describe the degree of ionization in solution. Strong acids and strong bases ionize completely in water, meaning essentially all of the dissolved molecules separate into ions. Let us first examine the strong acids listed on the slide: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and sulfuric acid. The first 6 of these acids are monoprotic, meaning each molecule donates 1 proton, or 1 H+ ion. Sulfuric acid, H2SO4, is highlighted separately because it is a diprotic acid and can donate 2 protons per molecule. When a strong acid dissolves in water, the ionization occurs essentially 100%. For example, nitric acid dissociates completely according to this equation. The single arrow indicates complete ionization. Nearly every nitric acid molecule separates into hydrogen ions and nitrate ions in solution. Because strong acids produce large amounts of H+ ions, their aqueous solutions conduct electricity very well and typically have very low pH values. Next, consider the strong bases shown on the slide, including sodium hydroxide, potassium hydroxide, and calcium hydroxide. Strong bases dissociate completely in water and produce hydroxide ions, OH-, just like sodium hydroxide. Hydroxide ions are responsible for basic properties. Again, the single arrow represents complete ionization. Calcium hydroxide behaves similarly. Notice that one formula unit of calcium hydroxide produces 2 hydroxide ions because there are 2 hydroxide groups in the formula. Since strong bases generate large concentrations of OH- ions, they have high pH values and also conduct electricity efficiently. Weak acids and weak bases ionize only partially, meaning that only a small fraction of the molecules form ions while most remain unchanged. Acetic acid, HC2H3O2, shown on the slide, is a classic example of a weak acid. The double arrow indicates that the reaction is reversible and does not proceed completely to the products. Most acetic acid molecules remain intact in solution, while only a small percentage release H+ ions. Carbonic acid, H2CO3, is another weak acid shown here. It ionizes stepwise. First, it loses one proton to form bicarbonate ion, HCO3-. Then, the bicarbonate ion can further ionize. Because these ionizations are partial, weak acids produce fewer hydrogen ions than strong acids of the same concentration. Unlike strong bases that directly release hydroxide ions from their formulas, weak bases like ammonia react with water to produce hydroxide ions. Again, the double arrow indicates partial ionization. Only a fraction of ammonia molecules reacts with water, so the concentration of OH- ions produced is relatively low compared with strong bases. Now, let's try an online activity to reinforce our understanding of acids and bases. Log in to the course site on D2L. Click the Content tab at the top. In the left menu, open Lecture Material, then select the module titled 18 Acids and Bases. Under that module, find Lab 18 Acids and Bases and download the lab worksheet. Complete it as you work through the online simulation. Return to D2L and under the same module, open Simulation, Acids and Bases. In the simulation, select the Intro window. Make sure to select Water, H2O, from the Solution menu and Particles from the Views menu on the right side of the simulation page. Lower the pH meter into the water and read and record the pH value of water. Check the chemical equation at the bottom of the simulation page and fill in the blanks in the worksheet. Count the number of H3O+ ions and OH- ions visible through the magnifying glass. What is the smallest whole number ratio between H3O+ and OH-? Note that hydronium ion, H3O+ ion, is a practical form of the H+ ion. Select strong acid, HA, from the Solution menu and Particles from the Views menu on the right side of the simulation page. Keep the pH meter in the solution. Read and record the pH value of the strong acid solution. Select weak acid, HA, from the Solution menu and Particles from the Views menu on the right side of the simulation page. Keep the pH meter in the solution. Read and record the pH value of the weak acid solution. Open the lab worksheet and complete Activity 1 and Activity 2. Note that these activities are intended to help you practice writing chemical equations representing the dissociation of strong and weak acids and bases.